Thank you, Craig. So, like everybody else, I'm enjoying being here. I thank you for the opportunity. What I'd like to talk to you today is the actual motivation is to understand this process of shear bending. Which is a quite amazing phenomenon in the sense that you exert strain on a material in a homogeneous way, and at some point everything is localized in one plane, and want to understand how and why and what is going on in this thing. And in particular, I would like to pay attention also to the fact that what you see is not always the same. They say depending on the loading conditions. For example, this is in compression and this is in extension. You can get very different angles of the localization line or band in 2 or 3D compared to the principal axis of the stress. So we want to understand what are these angles. In experiments, it turns out when we look at all the literature, angles that were reported in the literature are between 30 and 60 degrees. Question is why not less than 30? Why not more than 60? I'll try to answer these questions analytically. So I was asked to give a pedagogical talk. In fact, already many of the issues that I'm going to discuss were touched here and there, so I shortened a little bit, but still, we want to recall that in crystalline materials, plasticity, as we all know, is carried by defects, dislocations, glide when you exert an external strain. Whereas in glasses that are completely disordered, there are no apparent defects or dislocations. The whole thing is a big defect. So there is an issue, how do you want to discuss plastic events, plasticity? And I'm going to do this sort of in a analytic fashion. I just want to make it very clear graphically what is the difference between the response of a crystalline and an amorphous solid to an external strain. So here the external strain is the same, simple shear. And if the crystalline material has no defects, and if it has also inversion symmetry locally, then when you do a strain, that all that is happening, you have an affine response of the crystal, whereas if you have a glassy material, as I'm going to make a little bit clearer in the next slide, the response is much more complex if you want to come back to mechanical equilibrium, and we need to use methods of nonlinear physics, statistical physics to deal with this. So what is plasticity in amorphous solids? I'm following the line of thinking that I learned from Malandro and Lux and Maloney and Lemaitre in order to introduce plasticity in the context of zero temperature and quasi-static phenomena in a somewhat careful way. So imagine that you have an atomistic system. It could be a binary mixture or any other mixture. In a moment, I'll argue that the approach that I'm going to discuss here is very general. But you have some particles, point particles, whose positions are xi, and they're interacting via some interaction, maybe Lennard-Jones, maybe other. And you have an external affine transformation they're going to parameterized by J. So this could be a simple shear or strain or stress. It just tells you how the positions of the particles are changing under the subjection of the external agent. Then, as I said, when you have a system that is amorphous, then after you do this affine transformation and you want to know whether the system is in mechanical equilibrium, usually it will not be. In order to come back to mechanical equilibrium, there is an additional non-affine transformation that needs to take place. Let me show this in a sort of graphic way. So here we have a binary mixture. This is really Lennard-Jonesiums. These are point particles. The size of the circle is only the range of interaction. And now what you do, you apply an external strain in the simple shear. So these particles now, the arrows shows you where the particles are going to go because of the external J that operates on the system. Now I did it. So everything has moved according to what we have applied from the outside. And now you look at the forces between the particles. So the forces were 0 before the application of the external strain, and now the forces are complex, random, and pointing in all directions. The system is not in a mechanical equilibrium, and if you want to bring it back to a mechanical equilibrium, there is a second non-affine step that needs to be done. Whoop, this is the thing. So I'll show it once more. So here is the simple shear that we're going to apply from the outside. I did it. These are now the forces, and now this is the non-affine displacement that's brought it back to a mechanical equilibrium in the sense that the net force on every particle is 0. So now we can do a little bit of analytics. The force Fi on every particle was 0 before, and I'm going to now parameterize the affine transformation by some gamma. So for example, in this case, x goes to x plus gamma y goes to y. So the gamma will just tell you how much I'm going to shear. So the forces were 0 before, and the forces after the game is finished. And I have also the non-affine response that annulled the forces. Now, the forces in this case are Hamiltonian, and therefore Fi is minus du dri. And since I have a linear relationship here between xi and ui, I can to first order take the differential with respect to ri or to the ui. It really doesn't matter. So this has to vanish. In the sense the forces were 0 before and have to be 0 afterwards. So we have this condition on this athermal quasi-static transformation. So now let's interpret what this is. This is a second derivative with one full and one partial derivative. So this will have two contributions. One contribution is the double partial derivative with respect to discrete u d gamma dy. This is the usual affine response that you have also in a purely crystalline material. And then there is the other contribution. The ui itself will depend on gamma. How much non-affine response there is will depend on how much this affine transformation has gone. And therefore, I now have the chain rule, discrete u, dui, duj, duj, d gamma. So now we have to interpret these guys. This is the famous Hessian matrix Hij. And this object has only one index. It's a vector. We call it psi I. That is known also as the non-affine force. So here we have an exact relationship. But can we use it now to understand what is the non-affine flow that is going to be affected by the external affine straining process? So what I want to do, I want now to invert this equation to get a formula for duj d gamma, and that will of course involve the inverse of Hij. So duj d gamma is going to be the inverse of Hij on psi I. Now, can I do this inversion? That depends. The inversion is okay as long as the matrix H has only positive eigenvalues. By the way, it is of course real and symmetric, therefore diagonalizable. So as long as Hij doesn't have a 0 eigenvalue, this is legal, and I can invert. So let's do it. So here I just inverted dui d gamma is minus Hij to minus 1 on psi, as long as no eigenvalue is vanishing. However, as we know, when you strain, there is the catastrophe that happens. That is, say, eigenvalues, these are typical eigenvalues in a small system, by the way. So some of the eigenvalues of the Hessian matrix don't care much about the relative strain, but some of them do care a lot, and they go to 0. They go to 0 via a saddle node bifurcation, which is generic and gives you a parallel singularity for the way that the eigenvalue goes to 0. It's always a square root, and the point where it touches 0 we're going to call gamma p. So you have the lambda p going to the square root of gamma p minus gamma. Now if this is happening, and it will happen at one point or another, then in that case I can expand, as long as it doesn't happen, say I'm here, I can expand the vector psi in the eigenfunctions of H. So this is the expansion. Now the eigenvalues of H appear in the denominator because it's Hij to minus 1. So this is an exact statement. And now when one of the eigenvalues become very small, this sum is going to be dominated by that fellow. And the projection will be dominated by the eigenfunction that is associated by this eigenvalue that is going to 0. So now we see that the non-affine field is dominated by the eigenfunction that is associated with the eigenvalue going to 0. This is an exact statement every time you have such an instability. By the way, this is a situation for a small system. In a large system, we know that the eigenvalues now go to a density, and how the density of these eigenvalues that are dangerous is characterized. This is the exponent we've introduced a couple of years ago that has been so beautifully and effectively used by Battier in his talk. But let's now continue to think about a finite system where there is a gap between these eigenvalues as a function of gamma. Okay, so we've learned that we have this. Now, what is the nature of the eigenfunctions? Well, we all know. Sorry? The sigma? The psi? Psi? Oh, yeah. They are not. They are actually. This vector is actually quasi-random, as one can argue. Psi. Okay, not sigma. Okay. Yes, it's true. So here's how an eigenfunction looks like. So this is really the eigenfunction. You can find the matrix. You can diagonalize it. You can find it, and what it does, it shows you the famous sort of quadrupolar structure that particles are streaming in and particles are streaming out. This is the displacement field, and whether you look at the displacement field or you look at the eigenfunction, it's the same quantity. So this is indeed a plastic event, and you can understand what it does, but we'll make more statement about the analytic form in a second. So I just want to say this is a very general approach. I mean, it's not only true for purely atomistic mechanical systems. You can do it also, for example, in situations we have magnetic interactions. We just looked in the last couple of years a lot at situations where the energy is a function of the positions, but also some of the particles have spins to them. And then, for example, you can look at the hysteresis curve, the Barkhausen noise, and you look at these instabilities. And then, again, you have a Hessian matrix, but just more complex. You have the second order derivative with respect to all the degrees of freedom, including the cross terms dri d phi j, where phi are the angles that are associated with these spins, etc. And then, you again have eigenfunctions that are localized in a region, but then you have a projection of the eigenfunction both on the positions and on their spin, and you can use this same kind of approach to understand what is going on in such cases. Let me also make the point, coming back to Bob's statement yesterday, that in his cases it looks different. It does. In those cases you have friction, and therefore you don't have a Hessian matrix. Instabilities are still there, but you need to understand what's the operator. When you understand the operator, it just these eigenvalues, eigenfunctions are concentrated on the force chains, and the breaking of the force chains is the instability. So it's very different physics, but nevertheless you can use a similar approach if you know what is the right operator, which you need to find out. Okay, but now what I'm going to use is the fact that has been already raised by a few people, that these eigenfunctions are also isomorphous to Eshelby inclusions. So as you know, Eshelby in the 50s has solved a totally seeming irrelevant problem to us, which is you take a elastic material, you carve a hole, you take the material out, you stretch it into an ellipse, and you stick it back, and then you get a displacement field or a stress field that you can find analytically. Eshelby has done this in an analytic fashion. And what I can do now, I can look at my system and find what is the eigenfunction that I see in the numerics, and I can fit at Eshelby solution, and this is an analytic thing. So the Eshelby solution now is for the displacement field that is around such an instability, and it's very useful because this gives us a lot of analytic power in understanding what is happening. I don't want you to look at the details here. I just want you to remember that for the case of a simple shear, and only for the case of a simple shear, I'll come back to this issue, this solution is parameterized by two parameters. One is the core size, A, which determines how big is this hole here, and the other one is the eigenstrain epsilon star. So two parameters parameterize this, and in order to do a theory for this object, I need to actually find these parameters epsilon A star, and they will depend on many things. Quench rate, potentials, God knows what, but for every particular system, they will have a rather sharp distribution around one eigenstrain and one core size. Okay, so now let's proceed. You've seen already before, yesterday in particular, that there is a very interesting change in the nature of the instabilities when you go up in the strain. Let's say when you are at small strains, you have blips, plastic events, but these are very localized. The energy of these scale like the number of particles to the zero. They're independent of their system size. However, when you go to larger gammas, you start to get large such catastrophes. And when you look at the energy in these catastrophes, this energy, the delta energy, increases in a non-extensive way, but as a function of the system size to some exponent. So there's something very different occurring here and occurring here. This is still an instability. Still the Hessian matrix will show what is going on here, and eigenvalue will go to zero, but the eigenfunction now is very different. And what the eigenfunction is doing now, it's doing something interesting. It now has a concatenation of such Eshelbys, or sort of a line of such things that I'm going to model here with a row of such Eshelby solutions that are appearing spontaneously instead of a single one. The question is why? Why is it localized? And what is the orientation? What's the angle it's going to show? That's the main question. And what I'd like to propose to you, that the fact we have an analytic solution for this object is very helpful, because now I can go and ask what is the energy associated with any distribution of n such Eshelbys. Okay, and you can see the details in these papers, but it's easy to say because we have a linear elasticity theory. We use elasticity theory, so you can write all the contributions. So here there is a contribution from the material that is strained with the strain epsilon and has a stress epsilon sigma. So this is the contribution that you get from the material itself, whether there are Eshelbys or not. Then you have the contribution due to the strain in the material and the strain in the Eshelby. So this is the eigenstrain that I mentioned for each one of them, and you have to sum up from I to n if you have n such guys. And then you have the self-energy of each one of them. So you sum on n contributions, each one, the strain, the eigenstrain, times the stress field that is formed around it. And then there is the interaction between these Eshelbys. So you have the strain of one times the stress of the other. And this, of course, will depend on the distance Rij between them. So you have n such guys. Now you want to know what distribution will they take. So what I want to propose to you, since we have at zero temperature, energy should be a good thermodynamic potential. We ask what is the cheapest organization that you can have. Now, this, of course, doesn't matter. This will not affect the distribution because it's independent of the Eshelbys. And you see there's only one term here that has a sigma infinity. So what we're going to do, I'm sorry, I want the one that has the gamma, which is also where it has the external gamma. So this is the only one where the gamma is appearing. So it's difficult to minimize all the energy of all these things. So let's start with very large gamma and ask what will be the prediction if we want to minimize this. And this is depending only on the orientation. You see these Eshelbys, which are quadrupolar, can look like this, or can look like this, or can look like, I don't know, any other sort of thing. And when you minimize this term, you see that the minimum is occurring when all of them are equally phased. That is to say, they are still not on a line, but they have to be all pointing in the same way. They just say their positioning should be all the same. So maybe one here, the other one may be there, the other one may be there, but they have to be all oriented in the same way. When you use this fact in the other terms, it helps a lot in this minimization. And you find that the global minimum is obtained where they are in a line, and when the line that is occurring is at a specific angle with respect to the external strain. For the case of simple shear, that angle is 45 degrees exactly. When you use all this, you can rewrite all these energy considerations in a simple way that depends only on the strain and on the density of these Eshelbys. And that has a very pleasing form, because it's a form that you will recognize very well. And it has a parameter that is gamma y, which we're going to call the yield, which is determined only by the eigenstrain that we know from fitting these objects, and this is the Poisson ratio. So now let me show you how this function looks as a function of gamma, and it looks like this. So for gamma smaller than this gamma yield, so when you are at small strains, it looks like this. So the energy is increasing when the density is increasing, and the only minimum is occurring when rho is 0. There's just a single one, as we see indeed for small gammas. Yes?
A couple of quick questions. You found that when they go unstable, they look like entropy inclusions, and that motivated you to think about entropy. You said that the moment of the entropy inclusions were all the same.
We are going to model this with a bunch n of identical Eshelbys. This is what I'm doing this calculation now.
And the latest calculation, you were investigating the interaction energies between these entropy inclusions.
So I have the displacement field. I have that displacement field, so I know the stress, I know the strain, so I can now compute for any distribution, any positioning. And then I'm trying to find what is the minimal value of that energy, how the cheapest solution.
And you're going to motivate how that minimum value affects the glass, where you're not allowed to move anywhere you want.
No, they are not moving. They're appearing simultaneously. Yeah, there's no dynamics. Yeah. Correct. This is maybe one of these selection criteria that Jim was complaining the other day that they don't exist. So maybe here there is a yeah. Okay. So what am I saying? I'm saying, okay, for gamma much smaller than gamma yield, the energy is increasing as a function of rho. So the only solution is rho equals 0, which is a single one, is what we see at small values of gamma. Then we are increasing gamma. This is still true, but there is a point which is at gamma equals gamma yield, as you can see from this formula. When gamma equals gamma yield, well, this is no longer true, and you can now have a finite rho. So we propose that this is a way to understand why the instability suddenly prefers to have these things. Now, you want to realize the following thing. When you have a single instability of this kind, okay, for example here, then you know that the displacement field is now falling off like a power when you go towards infinity. Okay, this is what you have. You have a quadrupolar structure, and the things are falling slowly when you go to infinity. Now when I have more than one, so this is, let's say, going out, and this is going in. Now when you have another one, let's say here, if you can see it, I don't know if you can see it. Can we, maybe I'll just go up a little bit just to see this. It's an important point, so I want to make this very, very clear, what is really happening in terms of the displacement field. Okay, so here you have one guy, here you have another guy, here you have another guy. So this is going out, this is going in, this is going out, this is going in, etc. So now you have a global connection. It's no longer true that it falls off to infinity. The incoming is going to the outgoing, and now this organizes the displacement field to be like this. So this is exactly what we saw, for example, yesterday in Bob's talk, that you have this concentration of the displacement field over a small region. Okay, let me now continue and try to go to the issue of the angle. So as I said, for a simple shear, the minimum that you find is at 45 degrees. Now, what about different angles? And what is the reason for different angles? Well, the reason is that the Eshelby, when you have, say, extension or compression, is no longer symmetric. That is to say, here I now have to introduce another number, not only the core size and the eigenstrain. I have also to tell you how much you prefer to come in compared to how much you go out. So let's call this zeta 1, and let's call this zeta 2, which is the rate of coming in and the rate of coming out. For a simple shear, zeta 1 equals minus zeta 2 exactly. It's a area preserving. However, clearly, when you compress or when you extend, this is no longer true. You can go more far than come inside. And then the Eshelby inclusion is no longer volume preserving. You can repeat the calculation with this additional parameter, and you find analytically that the angle, the cosine theta of the angle, is 1/2 plus this combination of the eigenvalues. As I said, when zeta n is minus zeta k, in this case, this is 0, and you have 45 degrees. Otherwise, you have a correction to the 45 degrees in terms of these eigenvalues. You can compute for every case by fitting the Eshelby to what you see, and you get actually very good agreement between what you measure and what comes out of this thing. So it's very simple. The angle depends on the external strain. The external strain will determine the symmetry or the asymmetry of these plastic events which are modeled by the Eshelby, and that gives you a very clear understanding of the angle. All right, can you generalize this to 3D? So I'm not going to go in great detail. Let me just say that an Eshelby circle now will generalize to an Eshelby sphere, but in fact remains two-dimensional. This is very interesting and very important. You see, when you do a shear, let's say, on a three-dimensional system, there's no force or there's no pulling or pushing in the direction orthogonal. And therefore, actually, the Eshelbys remain pancakes. They're quasi-2D. And then what you find when you do the analysis that the line of Eshelby quadrupoles generalizes in this case to a plane of Eshelby ellipsoids. And the calculation predicts that the minimal energy arrangement is for quadrupoles living on a triangular lattice on a localization plane. So now it's not a localization line, it's a localization plane. My student Kamel Shor, in a heroic numerical effort, actually could see this by looking at careful numerical simulations. He found where these Eshelbys are, or these quadrupoles live along and across a system that is shear in this way, and indeed they live on a triangular lattice to a very good approximation. So it's a simple generalization, even though the calculation becomes much larger. Now let me finish by asking, okay, all this was done for 0 temperature and quasi-static. Can you learn anything from this to finite temperature and finite strain rate? And I'm referring now to this amazing law that was found by Bill Johnson and Conrad Sommer that have measured carefully the yield strain as a function of temperature and strain rate in relation to this yield strain that I just discussed with you that appears at temperature 0 and 0 strain rate, and has a somewhat strange formula in the sense that it has a temperature dependence at the logarithm with a 1 over gamma dot to the 2/3, a little bit unintuitive law, but seems to fit the data pretty well. So how would you do this? Well, what I want to say is the following. If we have a situation like this, then as I argued, you're never going to see localization on a line or on a band when gamma is smaller than gamma y. But imagine that you're here and you have a temperature. Then you can escape over this barrier. And I can, since I know the energy, I can estimate the time it takes to escape. And if you do a calculation that every one of you would have done in this case, which is by the way, I have, of course, to say that if you have finite temperature and 0 strain rate, since you have temperature, you always have a probability to flow, so there's always yield. This is well known. I mean, there's always a yield even at 0 strain when you have a finite temperature. But what we want to understand is the situation where you have also a strain rate. And then a finite strain rate can occur only when the time that you would compute for escape over the time barrier times gamma dot is the order of unity. If you use this and you use the theory, I'm not going to go all the details. You can read it in this paper. It's explicit. You find the same law exactly analytically, except that the coefficients that were fitted in the experiment A, omega 0 C are now computable. They are computable, and here you see the relationship that we find in numerical simulations between the law and the actual measurements of the yield as a function of temperature for a given gamma dot, and there's no free parameter here. There's everything is computable. So I think it's time, exactly, so I'll thank you very much for your attention. Don't say it was a nice lecture.
Nice lecture. I have two questions. As you know, for biometallic glasses, tension and compression, the angle will be different. Can you model this kind of situation?
If you tell me what is the shape of the plastic events or the eigenfunctions of the Hessian, the answer is yes, because then I just use it. It's a fit, right? I mean, I have to know what are the parameters of these solutions. They give me the stress field, the displacement field, and then the calculation just follows. So the answer is yes. But I need to know this data.
Thank you. And
it's not predictable, right? I mean, I have to know it from something.
Thank you. Second question is that, as you know, when the shear band propagates, using your model, can you predict the temperature in the shear bands?
I have to be careful. You see, and this is something that is not obvious until you think about it deeply. You see, this is not yet a shear band. This is a localization of the plastic phenomenon. And the reason is that we're doing quasi-static. Quasi-static meaning that after I reach the instability, I take the system back to mechanical equilibrium. So I go up and then down, then up and then down, up and then down. This is very different from if you do stress control. If you do stress control, you go up there to the point that is highest, let's say, and then, okay? That thing we're studying now, and I don't have yet anything clever to say about what is different. Okay, so this is a micro shear band. It just makes a little okay, and then again and again and again. It's different from stress control where you can really collapse and break. It has to be very clearly stated. It doesn't correspond yet to macroscopic yield because of the procedure of quasi-static. Yeah. So we are now working, and it's not easy, by the way, to do proper stress control. I mean, I spent 6 months thinking about how to do a stress control, and I quarreled with around several times how to do this. And I think now we have a good procedure to do stress control properly that I can trust. And it's a beautiful thing. You know, you really get there and you collapse. And we're now studying this. So, but I don't have much to say yet. It's still in the numerics stage.
The picture of the SLB array that you had, so I have a question about that. Actually, a couple of related questions. No. You went too far back. If you go forward towards the end of the talk. The 2D.
Analytics?
No, the 2D array that
Here.
you had.
Here.
Keep going. I'll tell you when to stop.
Oh, the three-dimensional.
Right. Well, the array is
Yeah.
2D. Yeah. So this one, I mean, you said it's in a triangular lattice, and it's not
in this plane. Okay, in this plane. You see, here, triangle. You have to go in this way. Okay. The way it works is this is now connected globally to this and this here. So the flow is now like this. Okay. You are shearing in this way. I'm sorry. You are shearing in this. You're shearing in this way. So now the flow is going to be in this way. Right. So you have 3 here, 4 here, 3 here, 4 here. As you see, 3, 4, 3, and this flow is in this way. Okay, that's the geometry.
So y is going into the board, right? So x,
what
y,
y
plane.
Yeah, this is x, this is y.
Right.
So along y, there is no straining.
Yeah.
Okay, so these are pancakes that are organized along these planes. Yeah. the Eshelbys are not quite spherical, so really pancakey.
So you're actually looking at a 3D array of these? No, I'm confused.
It's a 3D, which is organized on a plane, which is the plane between the flow above and below. And on the plane, this is a triangular lattice. This is the minimal energy solution from the
in the
analytics.
XY, yeah.
Yes.
Okay, so I have to think about it, but the question I had is, if you have, like I said, the that's why I'm getting confused. That's why. Okay, but I won't take too much time. But the question is, if in whatever plane you think it is triangular, but this is. So what you show here is not a very convincing triangular lattice.
Remember, this is what we found from the numerics,
right.
And there's randomness and there's finite size effects. Correct. So it's as close to a triangular as I could hope.
I understand, but if you have some sort of regular structure in mind, is there a way that you can actually start with that, and you can certainly compare energy?
You cannot start. Right? Can you start the calculation?
Yeah.
No, the calculation of the minimum you can do.
Sure.
You can put them in any organization. And this, I vouch you, will be the minimal solution. That we found. Okay. Now, whether this is what you see as the eigenfunction that appears miraculously, simultaneously everywhere with the randomness and the finite size effect, this is as good as we could hope. Right? So there is some non-ideality in the triangular lattice here. But I think it's rather convincing.
So this is more of a follow-up to the answer to the previous question, which was, so you mentioned that it's in your opinion, persistent shear bands are happening because you're under stress control. But I think it's clear in MD that we see shear bands forming under strain control as well.
All that I can say that with this quasi-static strain control, you cannot have, because you go back to a mechanical equilibrium.
But that may have a lot to do with how the system was prepared prior to the
No, it's
shearing.
the way how you actually strain it. So you strain and do energy minimization. Strain, energy minimization. So when you have an instability, you force the system to go back to equilibrium.
But I mean, I think that's very counter to how I think about how the microstructure of the material evolves, in that every time you have one of these Eshelby events, it's not clear you leave the material the same way you found it. I think that softening is critical to how the shear bands form.
Possibly.
So I think
possibly.
Possibly,
but still, I say the crucial thing is that you have an instability where instead of having a single Eshelby appearing now in the eigenfunction, you have now an array. And that is independent of what you say. Maybe it'll come later or earlier or because of softening, God knows what. But you have this instability, you can analyze it analytically with the Hessian, and you can find what is the eigenfunction. It looks like this. The eigenfunction really looks like this.
Can I, am I next? Or?
Yeah, Jim.
Because I just want to sort of follow up what Michael Falk was saying, but also having promised Itamar that I would tell him what I didn't like about the talk.
Please. He says it was a good lecture. Go ahead. Go ahead, Jim. Go ahead. No, I'm kidding, Jim.
I think it was fine.
Okay.
But I do want to emphasize just a couple of points. You start with a picture of one of those.
But I said immediately that this is a motivation.
It's a motivation,
sure.
Yeah. But
where I want to understand the localization. Sure.
We had a lovely talk here a week ago. We had a lovely talk here a week ago from Wendy Wright, who was actually doing those experiments, and I pushed her pretty hard. I mean, do you see anything like what Itamar is telling us we should see? And she says no.
She should look.
No, she does.
This was the same answer that Bob gave. You don't see the post-strains because you didn't look.
Okay.
Yeah.
The fact of the matter is that real shear bands, as Michael was trying to emphasize, as they form in that picture, leave a permanent.
Jim is absolutely right.
Yeah.
But as I say, you cannot do it with this particular protocol.
That's exactly right.
This is why I say motivation to understand the localization and the angles.
Okay.
Now, you want to do what you want. In my laboratory, you have to be stress control. I cannot do it. I mean, in a controlled way. I don't want to do with temperature and gamma dot and lose all the. I want to do basic, careful stuff to understand exactly what is going on.
You need to be able to predict what happens under strain control, which is how the experiments are done.
Jim, I don't have to do anything. I'm a free person.
No, you don't.
I can do what I want.
But I'm talking about the moral obligation.
I have no moral obligation. I threw all my moral obligations when I was 18 and went into the army.
I noticed that, but I didn't want to. Okay.
But you know,
We've known each other for a long time.
the army was 3 years. I lost all moral obligations.
Okay, but look, I'm the only person in the audience, I'm pretty sure, who actually sort of knew Eshelby. All right? But
Did you?
Yeah, he was at Birmingham when I was a
It's a
student.
fantastic paper.
Yeah, and that's the paper. I didn't know that he was going to come back and haunt me like this. Another point that I wanted to make, in addition to the fact that what you see in these AQS simulations are not yet realistic shear bands.
Accepted. I would be the first to say it.
And the next thing I want to point to, because Conrad Somewhere is here, is that I want to point out that, in fact, forming shear bands is not what he sees as as the yield points. That's a very different phenomenon.
Conrad, do you want to respond?
Well, let me say first something about the actual inclusion and the organization of that, actually. In the colloidal system, Peter Schall and other people, Franz Barpen, David White, they see that actually. They see the organization of the inclusions, STZs they called, or branches in between actually, which line up to see actually what Itamar was calculating here too. The question is, what I have actually for that is, now since you have the triangle lattice, this remembers me to flux lines in superconductors.
That is correct.
And so you have the coarse-grained model. Actually, you could melt now these flux lines, this triangle lattice of fluxes, into a continuous behavior, homogeneous flow. And so that is actually the starting point to go on beyond that one, what we just discussed here.
Well, I insist that in my way of thinking, I have to go stress control, because then it really collapses. In my way of thinking. Because I don't know how to do it in strain control in a way that I control. Strain control squared. That's the strain control and my control. I don't know how to do it. But stress control works. So that'll be the next lecture next year. Mike.
So perhaps everyone is trying to ask the same question. I'll try again. There could be a form of selection bias in this presentation, where because you want to illustrate the power of quadrupolar disturbances, you select the cases which make them look the best.
I didn't really select.
Okay, but the
These
question...
are the same models that everybody does, right?
Yeah, but so let me ask you to reverse it. If you think about the times when you tried to fit it to this representation and it worked the worst, what were those cases like? And was it simply a matter of changing loading rate, or do you think you have to change the microscopic physics
There's
in
no
order to
loading
make
rate
this
here.
breakdown?
There's no loading rate here. This is quasi-static. So no exception. You changed the model, you changed the potential, you go A, B, M, or whatever you have, it's always doing the same thing. However, if you change the interactions enough, take hard spheres or any of these sort of jamming things, or especially we have friction forces, entirely different physics. You still can use the ideology. Find an operator that controls the instabilities, look at the eigenvalues, I think it's very useful. The magnetic cases, again, very different. We looked carefully at the case with the magnetic cases where the instability involves a flip of a magnetic domain. I don't know how to do this because I don't have the Eshelby solution for the spin case. So I cannot follow this program. Okay, so there are many issues, and it's not always the same independent of what you do. So I think that one has to be careful to the differences. And this was Bob's remark yesterday. Not everything is the same. You have a different system, different laws, different operator. Hamiltonian doesn't exist. You have friction. Forget this. You have to start from the beginning. And you'll find something different. You'll find force chains, you'll find the breaking of force chains, etc. But the philosophy, let's try to understand atomistically what is the operator that is controlling the stability. Then you don't give names. You just have eigenfunctions and eigenvalues. You don't need to be vague. Everything is clear.
Quick question. When I was looking at the talk, I think I may have missed something important. This is a simulation?
Yeah, of course.
And in that simulation, you got this triangular lattice
Yes.
of these Eshelby inclusions.
Right.
That's very illuminating. Thank you.
So, when we've looked at the same sort of systems, what we've seen is that most of the eigenmodes are in fact very localized, even when there are large events. So the eigenmode will be very small, a single Eshelby inclusion, and what actually happens is that when it goes unstable, triggers a series of other eigen.
I don't know what is the meaning of the word trigger. I mean, here an instability occurs when the eigenvalue goes to 0. Period.
Right. So the
It's not
eigenvalue.
triggering.
Okay.
No words.
May I?
Yeah, please.
So the eigenvalues tend to have a characteristic size,
Right.
and we don't find eigenmodes which correspond going to 0 very often that are spatially extended, even though.
I think you had sub-extensive events.
Let me be. So I'm saying that the mode that goes soft, the zero frequency mode, is localized, and does not have the same shape or extent as the final instability.
Exactly. Yeah, I agree.
And so what seems to happen is that there's an Eshelby, something like an Eshelby inclusion that's becoming unstable, linearly unstable, and as it does, because of the strong interactions you're talking about that are directional, the other Eshelby inclusions have their modes.
Simultaneous or?
Not simultaneously.
Yes, precisely.
Okay.
And so it's not, it wouldn't be, you wouldn't see all of these Eshelby modes going soft in this structure at once. They would go sequentially. And the coupling you're talking about is what means that preferentially the sequential order will be along the specific
we need to look at this together
direction.
because we certainly see them appearing simultaneously. No, we don't have time. Of course not.
I would love to say
you doing
something,
it in gamma
but I'll
dot?
defer to Lisa.
We're doing it zero strain rate, but there's
So there's no time.
Okay, so
What time?
there's time, right?
What is the time?
I think Lisa will probably.
Mark actually asked exactly one of my two questions, so that's great, because that means because I see exactly the same thing he just mentioned as well. But I wanted to press you a bit on sort of your emphasis on eigenfunctions as being the thing to look at, because it's not clear to me that looking at the orthogonal modes actually gives you the entities that you want to be looking at, because when you diagonalize the dynamical matrix, you find out about the curvatures of the potential energy landscape. And what you're actually interested in is the energy barriers. And in particular, when I look at this thing, I know that you've said that there's one mode that goes to 0, but actually it looks like there's a mixing between the second mode, the second lowest mode, and the first lowest mode.
So what?
A mixing, because you see they approach each other right there.
I'm actually interested in this region where there's no issue. What?
So if I look at it, because actually what I have done is I've looked
Maybe there is a system crossing here, possible.
Yes, and actually, in fact, you can look at overlaps between those two modes and see that there was a crossing.
I'm only talking about the localization when you're very close to lambda equals 0. I don't care whether it came from the eigenfunction here, it is delocalized, or the eigenfunction here is delocalized. One has to stress, all the eigenfunctions are delocalized at 0. So, so one of them gets localized here. And as you see from this calculation, which is exact, there's no question that the one that goes to 0 is dominating the non-affine field. There's no issue.
Right. My only point is that what you're saying is that there was an energy barrier associated with some feature.
I didn't say energy barrier. Where did I say energy barrier?
Well, it had to. We can continue this conversation later. My only point is that I'm not sure that thinking about eigenfunctions is necessarily the right object here, because there's some subtleties to that.
Okay, I find it extremely useful, because then the discussion is concrete, and I know what I'm talking about, and I can do calculations, I can come up with explicit answers and results, compare them to the simulation. It seems to work very well, not just in this system. It's a very general way of thinking about, what is instability? Instability is an operator. Eigenvalues go through the imaginary axis.
She thought about this line.
I'm sure. I'm sure. But nevertheless, yeah.
Okay, so
I mean, it's a lovely perspective, and I understand it, but I'm just saying perhaps you could learn even more if you sort of extended beyond eigenfunctions.
So let's have one more question from Takeshi, and then we'll have to reserve for coffee.
I think the key is that the zero of Hessians are very unstable.
What do you mean zeros are unstable?
It changes a lot. It may be zero at the one configuration, but if you add a little bit of displacement of some atoms, it goes away. And zero appears at other places.
Possible.
And in the beginning, initial the process of this deformation, that certain atoms move quite a bit. It's not a fraction of angstrom, but sometimes 1 angstrom.
Okay.
So in this case, the harmonic expansion simply doesn't work, right? So it's a simple system is extremely unharmonic.
I think at temperature zero it works very well.
Yeah, but Hessian itself, Hessian matrix itself changes a lot. So what she's saying
Upon
is
what? Upon what?
By deformation, local deformation.
Of course. Well, of course.
Therefore,
the eigenvalues.
The initial zero doesn't mean anything.
No. It's not initially zero. It's not initially zero. It becomes zero at some value.
So I think in the interest of time, we should probably
Okay.
reserve
Anyway, I
the
agree.
discussion. It's going to be a very, very interesting
Understand.
coffee break after Sri's talk. So why don't we thank Itamar again, and Sri can come up and give the next talk.